Hey everybody, John Grimsmo here, and today I want to talk to you about breaking tools on the Kern. Now, we've been able to avoid broken tools almost entirely, and we run that machine 24 hours a day, non-stop, in a perfect world, and we try to avoid broken tools. But this tool has broken now 2 weeks in a row on the exact same component, which leads me to investigate. Something's wrong, and I want to figure out what it is. So let's jump into the Fusion 360 and try to figure it out. So this morning when I woke up, I logged into my computer to check on the Kern, make sure it's still running, because I knew it should be running until about 7 a.m. this morning. And then about 7:30 is when Steven comes in and unloads it, and I saw that a tool had broken last night, so I'm like, I lost a bunch of run. So I asked him to take this picture for me before he starts unloading things, changing anything, whatever, so that I could see what happened, because the same thing happened last week. So if you zoom in onto this picture really close onto that one hole, you can see that there's a step at the bottom of that hole, which tells me an end mill is plowing a little bit deeper than it should, and it's a very delicate, small 1/16 inch end mill, and I don't like that, so something's wrong. So let's jump into Fusion and see what's going on here. So here we have our CAD model, kind of stripped down to just show the clip right now. This is a 5-axis machine, so it doesn't have to be vertical. I can tilt it sideways, and I can have my coordinate system facing upright. So you can see here the coordinate right there is, Z up. So we do a bunch of operations. Drill specifically is where we got some issues. So spot, drill. Now drilling puts this tapered hole, like bottom to the hole. And when we take in our thread mill, you can't like plow that thread mill into the bottom of a drilled hole. So we come in with a little end mill. Let me hide some stuff here. Hide everything, clean it up nice and clean. So that thread mill needs a flat bottom hole to get very, very close to the floor. Otherwise, we're going to have problems. So what are we doing here? We're drilling a hole, and then we're coming in with this tool path. This is our next tool path. It uses a 1/16 inch 4-flute end mill, and this exact code has been running for a year or two. So the fact that we're having problems now is kind of weird, but it leads me to investigate and be like, no, this isn't right. So if I go simulate, give it a second to calculate. Okay, so we have a drilled hole. This tool goes to here. If I go to the info pane, I can see my feed rate goes from rapid to feed. Now I'm feeding down to 13 inches per minute, which for a tiny tool is not slow. Feeding down, slightly off center, feeding down, pretty fast. Okay, here's where we're starting to plow. I do not like to plow end mills if I can avoid it at any cost. Oh, plowing pretty hard and pretty fast. Actually, why is our feed rate 39 inches per minute? So this first straight red line is coming down at 13, and then I think I know what's going on. It's got a vertical lead-in radius where the tool is coming down at an archy angle. And that archy angle is going at 39 inches per minute because that's what I want to profile the hole at. So this is a heavy cut for this little tool, and I'm a baby. I like to baby these tools. So this is bad. We are plunging straight into the material. This is titanium. You don't mess around with titanium. Like, titanium is extremely unforgiving. So you have to baby it. That's why drilling is the most effective way to remove material. Always drill your holes, plunge the end mill into the hole, baby it around. So plunging, I don't like. I don't like ramping sideways at full speed. Look at how thick that sidewall cut is at full depth, or like full diameter. I don't like this. The sidewall thickness that we're cutting on the wall is only like a few thou. I don't mind that at all. But this depth at the bottom, that's what broke the end mill. And I guess that end mill's just been hanging in forever. I mean, that tool gets replaced probably every few days because of some end mill wear. And maybe the end mill wear's from this. But we have a schedule where we replace that tool every, I don't know what it is, 80 minutes or something. That gives us good life. And then it goes around the hole a couple times, and then comes back out, leads out. Okay, so that's a problem. So we have two options, two ways to fix this. Either we can do a spiral helix down, I'm going to move this next toolpath above. What this does, simulate, give it a second. So this tool takes 12 seconds, whereas the old one took 2 seconds. We're adding 10 seconds to our operation. Now, process reliability, I will take as long as it needs to not break end mills. But 10 seconds, let's see what we can do here. Spiral down. So let's go back a couple. So notice we're plunging into air, which I like. We're ramping down. We're feeding. Now we're at full speed, but the floor is not really touching yet. Starting to touch. Sidewalls touching. Now we're ramping down, and we're ramping down. I don't mind doing this. It's not my favorite way to enter a hole, but because this corner right here will start to chip end mills, it just puts a lot of excess wear on the end mills. You know, helically going down a hole works, but I find that it does wear the end mills over time. So this way works. This way should give us decent tool life, and better than plunging and hogging like we were doing before. So, but we're adding 10 seconds. That way is okay. Now, I used to have this problem on our Rask handles, which is the bit of code directly above this. How did I fix that? I started using a flat bottom drill bit. So here's our Rask handles. So you can see what's going on. Let's see, so we spot, drill our shallow holes, drill our deeper holes. I'll go front view. So here's our shallow holes. This is the threaded hole like we want. If, for example, now a flat bottom drill bit is an actual drill bit, but it's flat on the bottom. So it's very strong, much stronger than an end mill if you're plunging straight down. Simulate that. It looks just like an end mill here in simulation, but whatever. But it acts like a drill, much stronger. So it just, all it's doing is it's cutting out those corners. You can see the previous and, before and after. Same exact depth, but just creating a flat bottom hole. Great. And with this flat bottom hole, I don't actually need to open the hole up any bigger because the diameter is already perfect. So I can then take my thread mill and come in and thread that hole perfectly. So what I'm going to do is I'm going to copy, let Fusion think for a little bit. Black bar means it's thinking. Okay. I'm going to copy that flat bottom drill bit from the handle code. I'm going to paste it into my clip section, and always paste it at the bottom, so you have to drag it up to where you want, which would be right above tool 59, which I don't need anymore if this works out. I'm going to edit that. I have to make my clip viewable again. So those are all the old handle holes that I was selecting. I can delete that, select hole. Sometimes you can turn on select same diameter so that you only need to select once. But for habit, I like to do twice. Tool orientation, everything should still be fine. Depth should be whole bottom plus 5/10. Drilling, wrap it out. Same speeds and feeds. Good. So I've now added a tool change. This operation takes 1 second. To like pop. The tool change still takes a couple seconds. The Kern doesn't have the fastest tool change, not like a Speedio, but it works. So I shouldn't need tool 59 now because, as we know, flat bottom drill bit will make the hole. So I am going to hide that clip again. I don't need this one because I was just showing you guys and it takes too long. And I can just suppress this one for now, so it's still there. So what we're doing right now is we're spotting the hole, we're drilling the hole, and we're flat bottom drilling it just to clean out the corners. I could eliminate the regular drill and I could just go flat bottom drill and plunge it right through, but I have seen some tool life issues with breaking the flat bottom drill by plowing it right into titanium, so I try to avoid that if I can. But the 140-degree tapered drill bits, they last so long. So I don't mind the extra tool change to drill the hole with a regular drill bit, come in with a flat bottom, just kiss the bottom, make it square, make it nice, and then I will show you what the thread mill does. I'm going to move the thread mill to right above the flat bottom drill bit just to show you simulation what this looks like. Hide my clip again. Okay, so if I thread mill without doing the flat bottom drill bit, thread mill goes right into the center of the hole. Thread mill always plunges right to the bottom. Ooh, look what happens there. It just plows right into that material. I don't like that. That would break a tool absolutely every single time. And then it comes down and it makes these threads. It comes around one time. And that's it. I think it does 2 passes, possibly 3. 3 passes, and then we're done. Okay, 4. 3 and a spring pass. Look at that. So that should be the solution to our tool breaking problem, is making the pre-hole more suited for the end mill so that you're not overloading the tool, whether it be the thread mill or that Tool 59 1/16 inch square end mill. So great. I've already solved this problem on the handles because I had this problem like last year, but I clearly forgot about the clip, so now I'm applying the same fix to the clip. So that's great. The other solution, which I want to implement, maybe it could be its own separate video, is like what happens when a tool breaks. If I set the option in Fusion, then after every machining operation, it'll retract, it'll go to the tool setter will come up, and it'll do a breakage check. Takes like 2 seconds, no problem. And if the tool is shorter than it's supposed to be, it'll flag the alarm, it'll stop the machine, and it'll say, hey, your tool's broken, I can't continue. Now you can set various options to what happens in that situation, but I generally, unless you're extremely clever, I like to stop the machine, because a broken tool can't make the next part, and you can't call a sister tool and remachine that part because there's almost definitely broken carbide inside that hole. So you don't want to do that. The best option, in my opinion, is to scrap the pallet, especially on a pallet changing machine, to insert some logic to be like, okay, the tool's broken. Maybe we have a sister tool, a redundant tool that we can go to afterwards. So let's put away this pallet. Let's call it scrap or error or something. Let's continue the schedule and call the next pallet, bring it in and schedule it and just continue running it. Hopefully that broken tool has a sister tool that can be used instead, and that can be locked, that tool, and then continue machining like nothing happened. And then you can flag that one pallet as like, you know, take care of this when you have time kind of thing. That's the logic I want to get to, but it takes some macro magic to be able to exit out of all of my subroutines, my subprograms, in order to get back up and go to the next part of the schedule. I know in my head how to do it. It's just, it takes a lot of work. And you have to edit every single code that I've posted to that machine at every single tool change line with some logic to jump the rest of the code, go to the end, go up a level in subprograms, like back out of your subprograms and continue. It's going to be fun to do, but totally worth it. I think it will be worth it because while we don't break a lot of tools, we break more than I want, and even just literally last night, lost 8 hours of production. That costs a lot of money. Like, that's a lot of parts that didn't get made, that could have been made. So that's my next stage of that, and I was just chatting with Eric about that, and he's like, yeah, you should really do that. And I'm like, it's complicated. And he's like, yeah, but 8 hours, and how many times has that happened? I'm like, yeah, it's a good plan, good idea. So that's that. But for now, at least it does stop the machine and gives us the warning. But hopefully we have solved this problem, so this tool should never break again. And I love it when a problem is recurring, which means there's a reason, and then you can find the logic and figure out how to avoid that, which I think we just have now. Alright guys, hopefully you learned something. I do want to do more Fusion tutorials. It's very easy to drag on with Fusion and just ramble and keep going, but hopefully let me know in the comments if this was enjoyable and helpful to you guys in any way. If you want any more specific Fusion videos, I want to get my team using Fusion more and more, so I want to teach more. So that's the plan. Alright guys, bye.